Ever wondered how your computer manages its memory? Today, we dive into the fascinating world of memory management, specifically segmentation. In the realm of operating systems, segmentation is a technique used to handle data and programs in a way that mirrors how both programmers and users conceptualize data. Unlike paging, which slices memory into fixed-size blocks, segmentation divides memory into variable-size blocks, or segments. Each of these segments represents a logical unit, such as a function, an array, or a module of a program. Think of it as a library, where each book represents a segment, and each book is different. Different sizes, different topics, different authors. This makes segmentation especially handy for organizing data and code in a way that aligns with their logical structure. Now let's delve into the nitty-gritty of segmentation. It involves dividing a program's address space into segments, each with its specific role and size. These segments are addressed by segment numbers and offsets within those segments. In our library analogy, think of the segment number as the book's call number, and the offset as the page number. A segment is a logical unit of the program, like code, data, or stack, each with its own set of permissions, like read, write, or execute. The segment descriptor contains the base address of the segment in physical memory, the length of the segment, and access control information. The operating system maintains a segment table which stores these segment descriptors and is indexed by segment numbers. When a program references a memory location, it specifies a segment and an offset within that segment. The operating system uses the segment table to locate the physical base address of the segment, adds the offset, and accesses the memory location. So in a nutshell, segmentation is like organizing a library. Each book segment has its own place, address, making it easy to find when needed. It's all about creating a logical and intuitive system to manage memory, enhancing both performance and protection. But as we will explore in later scenes, it's not without its challenges. Now that we understand what segmentation is, let's delve into how it works. Imagine you're reading a book. Each chapter represents a segment. The table of contents is much like the segment table, guiding you to the right chapter. The page number within the chapter is like the offset. Let's put this into the context of a computer system. When a program references a memory location, it specifies the segment, or chapter, and the offset, or page number. The operating system looks up the segment table, finds the base address of the segment, adds the offset, and voila, it accesses the memory location. This is known as address translation. But what about security? Each segment descriptor includes protection flags that define how the segment can be accessed. It's like a security guard at each chapter, checking whether you have the right permission to read, write, or execute. This mechanism, known as memory protection, helps prevent processes from accessing chapters they're not supposed to. But what happens if a process tries to sneak into an unauthorized chapter, or tries to flip to a page that doesn't exist within a chapter? Well, the computer equivalent of a loud alarm bell rings. A segmentation fault occurs. This is essentially an error message that triggers an exception, stopping the process from causing any damage or confusion. So in essence, segmentation is like a well-organized, well-secured library of information. The operating system assigns each segment a unique identifier, much like a unique chapter title. The segment table, our trusty table of contents, maps these identifiers to physical memory addresses, and the offset, our page number, guides us to the exact location within the segment. This process ensures that each program runs smoothly, with each segment securely stored and easily accessible. So the next time you're reading a book, remember, you're not just enjoying a good story, you're practicing the principles of computer segmentation. So, what makes segmentation so special? Why use it? Well, let's delve into the benefits of segmentation, which are numerous and noteworthy. One of the fundamental advantages of segmentation is its ability to provide logical organization. Segmentation allows programs to be divided into units that have a logical meaning, such as a function, an array, or a module. This structure mirrors the way programmers and users conceptualize data and can significantly improve the readability and maintainability of programs. It also enhances error handling, as errors can be isolated to specific segments, making them easier to identify and correct. Let's take an example of a large software application. With segmentation, functions related to user interface can be grouped in one segment, database operations in another, and business logic in yet another segment. This division allows developers to navigate the program easily and make changes without impacting unrelated parts of the code. Next, we have protection. Segmentation plays a crucial role in maintaining the security of a system. Each segment can have different access rights, and these rights are stored in the segment descriptor. This mechanism prevents unauthorized or inappropriate access to memory segments. For instance, a segment containing sensitive data can be set to read only, preventing any modifications to that data. Finally, let's talk about flexibility. Segmentation offers a level of flexibility that is not available with other memory management techniques. Segments can grow and shrink independently, which is particularly useful for data structures like stacks and heaps that change size dynamically. Consider a stack that grows when new elements are added. With segmentation, the stack can expand into the free space adjacent to its segment without any need for relocation. Thus, segmentation offers an intuitive and secure way to manage memory, accommodating the dynamic needs of programs. Despite its challenges and limitations, which we'll cover in the next scene, segmentation remains a powerful tool for memory management in operating systems. Like any technique, segmentation has its own challenges and limitations. Let's dive into them. First, let's talk about external fragmentation. This is a situation that can occur when memory is allocated and deallocated in different size blocks over time. As segments of varying sizes are loaded and removed from memory, they can leave behind pockets of free space. Imagine a bookshelf where you've removed some books and now have gaps between the remaining ones. You might have enough space overall for a new book, but not in one continuous spot. That's what happens in memory with external fragmentation. The total free memory might be enough to store a new segment, but it's scattered throughout, making it difficult to find a contiguous space for the new segment. This can lead to inefficient use of memory, and potentially even an inability to load new segments, even though there's technically enough free memory. The second challenge is segment table overhead. Remember how we mentioned that the operating system maintains a segment table that stores segment descriptors? Well, the larger your program is, the more segments you'll have, and hence the larger your segment table will be. Each segment descriptor, containing the base address, length, and access control information, takes up a certain amount of memory. So the more segments you have, the more memory your segment table uses. This can have an impact on performance, as valuable memory resources are consumed just to keep track of segments. It's like having a massive index at the start of a book. It might help you find things, but it also takes up a lot of space that could have been used for the actual content. In conclusion, while segmentation offers a lot of benefits, it's not without its challenges. External fragmentation can lead to inefficient use of memory, and segment table overhead can consume valuable memory resources. These challenges, while significant, do not overshadow the numerous benefits of segmentation. Let's recap what we've learned about segmentation today. In the grand scheme of operating systems, segmentation plays an essential role in memory management. Unlike paging that slices memory into fixed-sized blocks, segmentation divides memory into variable-sized blocks, or segments. Each segment represents a logical unit, such as a function or a module of a program, making segmentation a highly intuitive and efficient method of handling data and programs. We've learned that the segmentation process involves dividing a program's address space into segments based on their logical functions. Each segment has its specific size, and they are addressed by segment numbers and offsets within those segments. These segments, segment descriptors, and segment tables form the backbone of segmentation. How does segmentation work, you ask? Well, the operating system assigns each segment a unique identifier, and the segment table maps these identifiers to physical memory addresses. When a program references a memory location, it specifies a segment and an offset within that segment. The operating system then uses the segment table to find the physical base address of the segment, adds the offset, and accesses the memory location. The benefits of segmentation are numerous. It allows programs to be divided into logically meaningful units, making it easier to read, maintain, and handle errors. Segments can have different access rights, offering a robust security mechanism to prevent unauthorized access. Additionally, segments can grow independently in size if needed, providing flexibility for data structures like stacks and heaps that change size dynamically. However, segmentation is not without its challenges. It can lead to external fragmentation, as free memory blocks may be interspersed between allocated segments, potentially making it difficult to find contiguous space for new segments. Larger programs with many segments can also lead to large segment tables, consuming valuable memory and potentially impacting performance. And there you have it, segmentation, a key technique in memory management that helps your computer run smoothly and efficiently.